we've got everybody, so let's begin. So at the beginning, I'd like to take this opportunity to thank the organizers of DevOps 2017 for having me here, and for all of you to come to this talk. The following are the lessons I've learned from having the privilege of working alongside world-class engineers on the most challenging scaling problems, ranging from the dissemination of knowledge in large-scale code bases to compilers, static analysis, and providing fast and actionable feedback on builds. So without further ado, let's begin. Very briefly, who am I? My name is Ryan Sonnenberg, and over the last 2 years, I've had 2 distinct roles at Uber. The first role I had was that of an Android systems engineer, looking at why the application crashes, why developers misuse APIs, and why things ultimately go wrong in production. The one area of focus that I had immense pleasure diving into was the issue of null pointer exceptions and why these ultimately reach production. And as a result, I went from kind of this role of reviewing source code, making sure that developers knew the best practices, to kind of disseminating this knowledge in a more automatic way. I dove deep into the compiler, into static analyzers, and as a result, I've walked away from the experience with a large passion for build systems at large scales. So the title of this talk is Building at Uber Scale, and those of you wondering what that even is, nothing exemplifies this more than this picture of my mailbox on the right here. For those of you with particularly poor eyesight, this is a desperate cry of help from my mailman, who's written on my mailbox, "Please mailbox full." What makes like a problem in my mind like Uber scale is you're looking at a system like this where like this is a full mailbox, this is a system that can't scale any further, and you know that you're gonna have to do like 10 times the number of letters in this mailbox in like 6 months from now. So you're kind of like racking your head for any sort of way to kind of like engineer yourself out of this problem. And we're gonna kind of look at all the techniques that we can to help accommodate systems to scale. As a brief exercise, we can kind of think about what is the scalable solution to my mailbox. And it should be pretty obvious that it's just email. There are a number of reasons why email is a preferable and a more scalable solution to the mailbox. Most obviously is that it can hold way more mail. Other reasons are just like it's much faster, it employs abstraction, a common pattern in large-scale code bases you'll see. For example, you'll see like a hash map abstracted into like an Uber hash map. In the same way, mail is abstracted into email. I don't need to know the ins and outs of spinning up a mail server to start up 20 email addresses. Another big reason why email scales so well is like my ability to write spam filters and to stop bad mail from coming in. And then another big win of the email address is I don't get passive-aggressive letters from my mailman. So all in all, it's a win-win. The other thing to kind of think about is that although email is the scalable solution over mail, it's not like a false dichotomy where it's one or the other. And I think in software, we too often fall into this trap of either everything has to be automated or everything has to be done by hand. I still need my mailman to come and deliver me packages, and I still want my email to deliver me mail. And kind of like the amalgamation of both the machine mind and the human mind is what ultimately leads to the most like efficient and effective systems. So without further ado, let's depart entirely from the world of mail and dive into the world of software. So during the course of this presentation, I'm going to be talking about the following ideas, and they all kind of fit into this theme of a problem that we faced as we started to bring in more and more developers into our pool, the different processes and systems that struggle to scale, and the ways that we mitigated these. The first category that we're going to be talking about is the dissemination of knowledge. Like, how do you teach people what the best practices are? And how do you do this as there are less and less veterans and more newbies entering your pool? The next thing we're going to talk about is the value of kind of like hunting down these small defects and that they ultimately have larger consequences at large scale. Something to think about is that the improbable becomes increasingly more and more probable as you do more and more trials. And as a result, you need to mitigate these small defects from creeping in. The techniques that we have are to kind of like provide railings and abstractions to prevent people from getting these defects in the first place. And then additionally, we have the build system and the compiler to rely on to kind of like detect anti-patterns and educate our developers on what the best practices are in the code base. After that, we're going to look at the value of speed on large-scale systems. And ultimately, what we're going to find is that if it's not fast, it doesn't scale. You need to provide your feedback, and you need to provide these type feedback loops in a way that is quick, actionable, and allows your developers to do the best thing as fast as possible. Then finally, we're going to look at what these methodologies meant for Uber, the improvements that we made to our own systems, and ultimately the impacts that we walked away with. So without further ado, let's dive in. So I start here with a Dilbert comic from Scott Adams. We have this senior developer, Old Johansson, who's whispering some technical knowledge into Wally's ears at work. The thing, for those of you that haven't read Dilbert, is Wally is the worst engineer at work. He's pretty pleased here because he's going to go lord this information over all of his coworkers' heads. The takeaway from this slide isn't that you can attain job security by keeping information from your peers. In fact, you should do the opposite of this. But rather, the thing to take away here is that teaching somebody a best practice is inherently kind of like a human pursuit. It takes typically somebody reading somebody else's code, saying, hey, I've noticed that you're misusing this API this way. Here's the correct way to use it. It takes a code review. It takes some kind of process, which what we'll ultimately see doesn't scale as things get larger and larger. This kind of process works very well when there is one Johansson to every single Wally. But when there are 10,000 Wallys to every single Johansson, it's just going to start falling apart. It's not feasible for Johansson to spend all of his time running around teaching best practices. And there are solutions to do this besides just word of mouth. So the most obvious way to do this and the easiest way is to hook into the build system. There are two reasons why there's so much value in providing dissemination of knowledge through the build system. The first one is that it has the full context of all of the source that you're working on. For those of you not familiar, the build system is the system that turns your source code into the final application. And in this system, you have the opportunity to look at every single line of source code that's being written by the developer. The second, more subtle reason why the build system is so valuable to the process of disseminating knowledge is that you have the eyeballs of every single developer when they're working in the earliest stage of development. You have the ability to change things, and you have the ability to take feedback and allow them to iterate it on it very quickly. The thing to keep in mind, though, when you're kind of trying to tie information into the build system is that there are two types of enforcements that you can provide. Typically, the build system is great at providing these kind of uniform, repetitive, and predictable types of enforcements. And the more nuanced types of refactors, or input, poorly written code, refactors to the Android activity lifecycle, need a human reviewer to come in. So there are a number of tools that will let you extend your builds to kind of teach your developers what the right things to do are. Examples of these are the error-prone compiler, the checker framework. You can even pass additional excellent flags into Java-C. There's the infer checker out of Facebook, and there's the checkstyle tool. And all of these can be used to extend your build to kind of teach your developers what the correct things to do are and how to detect your anti-patterns. So you guys might be wondering, can't I just detect all my, what's the point of diving into the build system this way? Can't I just teach all my best practices through code review? And I think the answer here is both yes and no. It matters ultimately what kind of scale you're at and how many lines of code you're asking your developers to review. The graph on the right is best explained by an anecdote from one of my very talented coworkers, Tony Conastetti. And what Tony will tell you is that if you give me 10 lines of code to review, I'm going to find 10 errors in the code. If you give me 10,000 lines of code to review, I'm still going to find 10 errors in the code. Pretty much the idea that an engineer can endlessly find defects in increasingly larger and larger amounts of source code isn't true. It begins to fall apart, and as systems get larger and as source code gets larger, it becomes less and less feasible to kind of provide this feedback through code review alone. I think a lot to my early days trying to reduce null pointer exceptions in the app. And when I started, I tried going entirely down the code review path. I wrote tons of code reviews that had nothing except add a nullable annotation. Is this nullable? What happens when this returns null? And ultimately, the thing to consider is that I was kind of doing the work as a machine of a machine, and then I was not letting the build kind of accommodate and pick up kind of the load that it could do. Again, it's really important to take the repetitive tasks that you're doing in code review and automate them to kind of free up your developers to go and supply like those more like nuanced refactors and those more like nuanced reviews to your code reviews. Again, like back to the example of like Wally and Johansson, an individual doing code review eventually becomes not enough in a large scale system, and you need to kind of get more methodical about it. Another thing to consider about getting very methodical in large systems is that as you start doing more and more trials, the highly improbable becomes increasingly more probable. The question I ask here is like, how often is 1 in 1,000 anyway? And the answer to that ultimately comes down to how many trials you do in a single day. The graph on the left shows the likelihood of seeing a 1 in 1,000 event over a number of trials. By the time you're doing 1,000 trials, you're already at like 40% chance of kind of seeing an egregious error. And as things get larger, as things get bigger, the likelihood that one of these small things coming to bite you actually becomes more. On the right here, I think a lot to kind of like cracks in a foundation and how tiny defects in a foundation are ultimately made worse as you put more and more load and more weight on it. So this is the thing to keep in mind as you're getting bigger, as you're growing, as you're doing more and more commits in a single day, as your developers are changing more and more lines of code. It's actually progressively more and more challenging to stay stable, and you need to get that much more methodical and that much more aggressive about guaranteeing kind of like a basic level of minimum quality assurance to the code that your developers are writing at. Again, I don't think that like this is necessarily like the heal-all solution to like every single developer shop. It depends on what kind of scale you're at, the number of developers you have actively working on your repositories, and then ultimately, as you bring on more and more, it just becomes more important to become methodical in this way. So like the next question is like, okay, we see the value of kind of like preventing these defects from getting into the code base, but like how do we prevent them? And there are two main techniques that I've seen that can lead to tremendous results for like preventing defects. The first one is the like value of like providing railings and abstractions for your developers. The idea here is that you're trying to scale up some process that is particularly error-prone. For us, it was onboarding new engineers who are trying to like spin up new repositories and get a quality continuous integration setup and a quality build system going. This was very tedious, this was very error-prone, and this process of like onboarding new repositories quickly turned from like a once-a-week task to a once-a-day task to like a twice-a-day task. It wasn't scaling. We couldn't keep up with kind of like the demand that like our developers were coming on. And ultimately, we needed a way to scale up the system. And the key to kind of scaling up this process was convention over configuration. It's tremendously easier to prevent errors if you ask somebody to follow a process as opposed to expecting them to understand the technical implications of what they're doing. The example that we have here is we provide like a bootstrapped Gradle plugin for other engineers to kind of lay out their own projects. And if they put their source files in the project structure that we expect, they're able to spin up like a large-scale like continuous integration setup without actually having to touch any of the code. We kind of provide them this like ironclad abstraction that they can then go on and use, and we can kind of like sleep safe knowing that the building blocks they're building on top of are defect-free, and they're able to kind of do these complex things without necessarily having to understand the technical details of what they're doing. Furthering down on this analogy of kind of providing these quality building blocks, I literally have a picture of like building blocks here. And the idea here is that you have one group of engineers building these like defect-free, rock-solid pieces of abstractions, and then you allow like other engineers to kind of build these like quality applications on top of them. The thing and the key to building like quality abstractions and quality railings is that they should enable your developers to do more as opposed to define what they can and can't do. Here on the right, Nathan Sawaya is able to build these like beautiful comic book statues without having to wonder like, what if one of my like tiny Lego pieces has a crack in them? He knows that what he's building on top of is rock solid. He doesn't have to understand how to manufacture a base building block. He can just go build something quickly and easily and know that it's defect-free. And by basically having this guarantee of our base building blocks in our systems, knowing that they're defect-free and don't have one of those tiny cracks, we know that we can scale, and we know that we can scale without the kind of like involvement of other engineers. So let's move on to like the second category of how to prevent defects from coming into the code base. And this is about like pattern detection, enforcement, static analysis, and diving deep into the compilers. As I said earlier in this presentation, I've been like particularly passionate about like getting null pointer exceptions out of our application. And the big observation is that this is not a task for a human being. You'll see this in modern JVM languages like Kotlin that have null safety baked into the compiler right out the gate. But if there is a predictable, a methodical approach to solving a problem, it's much easier to find a way to kind of like get man and machine to work in tandem. There are a number of tools that can actually help you if you're in a Java world that is struggling from null pointer exceptions. There's FindBugs, there's the Eradicate tool from Facebook, and there's even the nullness checker out of the checker framework. There was a presentation in here earlier today about exactly solving this issue. Again, the kind of like code path that we've always gone through and the kind of process that we've gone through in my own methodology is it's okay for an issue to reach production once, but it should never reach production twice. If you have these methodical things and these repetitive things that are constantly biting you, you need to look and say, like, is this something I can automate? Is this something I can teach a machine to look for? And if you can, do it. You'll eradicate those issues forever. So you might be wondering, how do I create these custom checks? How do I teach a computer to do code review? The secret to this one lies in hooking into the abstract syntax tree of the language that you're kind of like working in. For those that aren't familiar, the abstract syntax tree is kind of like it's a representation of the source code that you're working on. We kind of have like the code snippet below, and as like a thought experiment, by visiting like all the nodes in this tree, we could very easily build a checker that made sure that every single operator is performed only on primitives and not objects. Like we could say that like if we knew that like x was an object, we could say you have to use the dot plus operator as opposed to plus. So like the thing here is like, yes, we can teach our build systems and our compilers to do these very complex and nuanced things, but we're never gonna be able to teach our compiler that like the code on this slide is like absolute garbage. The variable names are terrible, it's like incomprehensible, and this is kind of like the key of like, you want your developers focused in their code reviews on providing the value to your systems that your machines can't. You want them talking about the testability, the maintainability, and the kind of like all in all design of what they're building. And you want your machines and your code review tools to kind of tackle the like repetitive and the boring cases, the cases that kind of drain your developers in code review and take up their like only 10 errors that they can find in a single cycle. There's a number of tools that can help you do this one. Every single language has their own tools to hook into the syntax tree. For Java, there's the error-prone compiler, there's a checker framework, and if you're doing Android, there's the Android linter, which comes with a whole boatload of custom checks. I've gotten a lot of value out of these and a lot of value of like providing feedback on these very like repetitive cases. A good example on like Android is there's like image views and there's like a content description for blind people to like, it will read out what the image is. You can just like add a lint check or a custom check that says, hey, you always need to fill this out. So again, the repetitive, the predictable, the things that are always biting you can be translated into the compiler. And the more nuanced things, we'll always rely on human beings to tell us that our code is no good. So now let's kind of depart away from like the source code itself and talk about speed. And the hardest lesson that I had to learn is that if it isn't fast, it doesn't scale. So we kind of talked about how you can build these kind of like defect-free systems or these defect detection systems to catch a wide category of issues. Like we could catch speed regressions, we could catch memory regressions, we could catch crashers in the wild. But if it isn't fast, it's not going to scale. I've been in the world before where you have the system that's detecting the errors in your code base after the commits land, after they've become coupled to the code base and after developers have built on top of them. And ultimately, if your systems aren't fast, you're going to turn into Charlie Chaplin below here, kind of like running into your coworkers, asking them to revert things, and you're going to end up in this like endless maintenance cycle of trying to maintain a system. And ultimately, this isn't productive because you're spending all of your time keeping a system alive Whereas you should be spending your time kind of building like that next big system, that next system that can detect the next category of issues. And you're going to get frustrated, and you're going to get frustrated with the kind of impact that you have. The other thing to consider is that when you're trying to provide feedback to a change, if it's not fast, you can't act on it. You can think back to the mailman example where like there's only a set amount of time between when he's pulling that like piece of mail out of his bag and it's going in my mailbox. Similarly, there's only so much time between when a developer is incubating a change and when it ultimately lands in the application on master. I like to think of like the kind of like common expression, which is like an ounce of preparation is worth a pound of cure. If you can stop things getting in, you'll scale. If you have to catch things after the fact, it's going to be a nightmare, and you're going to get stuck maintaining a system for your entire career. It's really painful, and this is really the value that speed provides you. So you might be wondering to yourself, like, well, how even do I make systems fast? How do I make them performant? There are three main categories for like how we've achieved success for providing speed in systems. They are don't do unnecessary work. This one's simple. If you don't need to do it, just turn it off. For the example of the mailbox that we started with, just don't send me mail that I'm not going to read. This would be like an ideal world, but again, if you're not going to need it and you don't need to use it, turn it off. You'll be way faster because of it. The next category of speed wins is to cache wherever possible. This is the idea that if you've done a unit of work, you don't need to do it again. If I have that target ad in my mailbox, just use the same target ad. Don't send me a whole nother letter. Finally, we kind of have this idea, and this is like the last kind of like paramount to achieving speed, is to like parallelize wherever possible. We could always make our systems more efficient by adding like more hardware, more cores, more threads, and you can just parallelize and make things faster. So like let's kind of like dive into how this kind of like lens helped us achieve speed wins on one of the tools in our systems. This is like the checkstyle tool. This is like a simple regex-based linter that you can use to assert things like file lengths, method ordering, and method names. The thing is, we were running this through a Gradle plugin, and we had to talk to the Gradle build system to get ready to run this tool. This thing ran in like about a minute in our largest code bases, and ultimately it ran every single time somebody wanted to make a change. This constituted about 5 minutes of developers' time every single day, and we made the following observations. First, we didn't have to talk to Gradle to get this thing ready. We could just turn off that whole process. We could call the jar directly and pass source files. We didn't need Gradle to build the source files. We didn't need class files. We could just go to the tool directly, turn off that entire flow, squeezed out like 3/4 of the entire performance. The next idea was that we didn't have to run this tool on the entire source set. We could cache. We could only run it on the changed file list. This kind of got us from like 15 seconds down to 5 seconds. And then with what we were left, we could parallelize it. We could run it on multiple threads. If we had 5 files, we could run it like across like 5 different threads. So as a result, we were able to take this like 5-minute cost on all of our developers and bring it down to like a couple of seconds. And when you do the math, the kind of like impact of these kind of changes are kind of staggering. If you have like 100 people going through this process every single day, you've claimed back like 8 hours. In the most like extreme way of thinking about this, like you're pretty much like saving lives when you create speed wins like this. You're kind of claiming back that like wasted time of a developer just sitting in front of a screen waiting for absolutely nothing to happen. You've like locked up their machine and you're getting that time back. Speed wins matter more and more as organizations scale and get larger and larger. And as you start squeezing these things out, and as you take this lens of kind of like turning things off, caching and parallelizing, you will see them in your code base and you will realize great impact. Let's talk about like another tool that kind of had us achieve these kind of same kind of like scaling wins. And this was kind of like the Okbuck tool. This is a tool out of one of our very talented developers, Gautam Korlam. And in his spirit, I ask you all, why does Buck always tip when it goes out for dinner? The answer is that because Buck always has the cash. Now that we've all collectively groaned at that statement, let's kind of like dive into what makes like Okbuck fast. Okbuck is a tool that turns a build system defined in Gradle and turns it into Buck. Where this was tremendously valuable is that Buck comes with a tool called the network cache. And this means that anything that was built on your servers can be used by another machine's cache. This means you build it once, and then you get the cache benefit everywhere, and we were able to squeeze like insane amounts of time into our build system. The other big reason, kind of like why this is so fast, is it's just much better at like utilizing the maximum amount of cores on your machine. It's fast because it doesn't repeat work, it caches wherever possible, and it exhibits strong parallelization behavior. And the reason why the Okbuck tool is really cool is that you get the best of both worlds between Gradle and Buck. You kind of get this like expressive DSL, and you get to write it in a JVM language, and you get like the fast and the network cache of Buck. It's a great tool. Go look at the GitHub page of Gotham's. We're trying to get it to 1,000 stars, so go like it. So like all in all, let's go back through and like summarize the like key ideas and the key issues and kind of like the key points of this talk. The first one is this idea and this challenge of disseminating best practices in your developer pool. And the key here is to hook into the build system. It's not enough to do code review. It's not enough to simply tell people what the best practices are. It's not going to scale. I've been there. I've struggled with it. You need an automated way to provide code reviews. The kind of like next big point is that small mistakes have big impacts at scale. As you get bigger and bigger, the improbable becomes progressively more and more probable. When I was an intern at Amazon, they had this great expression that says 1 in a million happens every single day here. As you get bigger and bigger and you do more and more trials, it's just going to become more and more challenging to keep them defect-free, and you have to become that much more aggressive about eradicating those simple mistakes. And then on eradicating those simple mistakes, there's kind of like two categories of techniques that we can have to mitigate these. The first one is quality building blocks, quality abstractions for other developers to build on top of that are defect-free. And then the second one is kind of hooking into the build system, hooking into static analyzers to look for the defects and fish them out before they land into the final application. Then we kind of looked at the value of speed, and ultimately we found that scalable solutions are fast ones. And like with like the final thought here and like the final conclusion is that we've been able to build our code bases larger and safer. We've been able to go from like a single, like every single repository is one module to kind of making a large monorepo of like 500 modules. And by kind of following these methodologies, by diving deep into caching, parallelization, and providing quality static analyzers to look for defects, we've ultimately been able to build larger and safer. And like our kind of like small repos build slower than our largest ones. It's pretty wild, and it's all a result of these kind of methodologies. So like, again, I thank you all for coming here. Like, I really relish and appreciate the opportunity to speak here. Thank you for coming. Again, my name is Ryan Sonnenberg. You can find me on like GitHub or Twitter at clonetune26. And then my work email there is ryansonneruber.com. Feel free to reach out if you have any questions on this category. Like, I'm particularly passionate about it, and pretty much just like open the floor to questions if there are any at this time. Otherwise, we can call it. But yeah, any questions? Cool. Thank you very much, guys.